Greetings and welcome. In this session, we will see a numerical on adiabatic cooling and humidification. In last or previous video sessions of HVAC, we have seen fundamentals of psychrometry, different properties, processes, use of psychrometric chart. With the help of that knowledge, here we will have one numerical which is based on one of the psychrometric processes. So here is a process adiabatic cooling and humidification. So for this process, let us have a statement of the numerical. So here statement of the numerical is given 10 cmm air, means here this air is given in meter cube per minute, that is a supply rate of the air at the inlet. Condition of the inlet air is given 37 degrees Celsius dBT and 24% saturation. dBT means dry bulb temperature and saturation means relative humidity. Is drawn through a desert cooler. Now to conduct this process, the device, mechanical device which is used, that is called as desert cooler, having an adiabatic saturation efficiency of 75%, means desert cooler in that especially humidification process is carried out. Thus desert cooler is acting here as a humidifier. So this value is humidifier efficiency. What is the final dBT and RH and how much water is required in kg per hour? So here the output is expected, that is the condition of air at the outlet of desert cooler in terms of dry bulb temperature and relative humidity. And to complete or to do the humidification process, the amount of water required, that is asked in kilogram per hour. So here this is a desert cooler diagram. In this is a air which is going inside at a condition of given parameters. Normally in a desert cooler there is an arrangement of spray water. So this spray water is sprayed in the form of small droplets. Thus when the air is passing through this chamber, it comes in a contact of that spray water and thus that air is getting humidified. So at the outlet we find the relative humidity higher than the relative humidity at the inlet. Now this process we will show here on the psychrometric chart. So for that purpose, the first point number 1 on a psychrometric chart with dry bulb temperature 37 degrees Celsius, from this if you go upper side in a vertical fashion, and this is a saturation line of 24% RH, relative humidity. Here we get intersection point number 1. Now from the point number 1 we have to proceed for this process, that is a adiabatic cooling and humidification. Especially this adiabatic cooling means what? Enthalpy scale. Here enthalpy is a same, enthalpy constant. So for constant enthalpy means what? We have to draw a line which is emerging from point number 1 and that will be perpendicular to this enthalpy scale, or that line will be parallel to the different lines which are here, WBT lines we say to that. So in this way if you draw this line, it will touch to this saturation curve at point number 3. So there this will be the 100% efficiency on the saturation curve. But as the efficiency given of this process 75% means point number 2, that is the outlet air condition, that we will find on the psychrometric chart. So on a psychrometric chart at the bottom here, this is a dry bulb temperature scale. So here we are given first point dry bulb temperature 37 degrees Celsius. So here is a 35 and 36, 37. So here will be that 37. So from this, if we go in upward fashion vertically and to reach this 24% relative humidity line, that is phi 1. So this line will be closer to this 25% relative humidity line. So here we will get this intersection point, that is a point number 1. So this point number 1 we have obtained. Then further process is what? As the process is adiabatic cooling, so it will follow the path along this line. We call this as a WBT line inside the saturation curve, and outside the saturation curve that line becomes enthalpy line. So this will follow the path, so in upward direction in this fashion. So this is a process where the parameter dry bulb temperature is decreasing and humidity, specific humidity is increasing. So that is why this process is a cooling, adiabatic cooling. And humidification. Here enthalpy is remaining constant. Now as this reaches to the saturation curve, here we will find the point number 3, and temperature of this point number 3, if you see here is a 20, so this is a 21. So TD3 temperature is a 21 degree Celsius. 21 degree Celsius. So this we will use to find the temperature of air at the outlet of desert cooler, because desert cooler, that temperature will be in between, as the efficiency of this humidifier is a 75%. So it will come here in between. So that we have to ensure with the help of formula. So in the formula now we will put the values which we have obtained now from the psychrometric chart. So whatever we have got, we have enlisted here also on chart point number 1, that is a entry point, and after doing the process, this is the from chart we get TD3 temperature. So from the chart we have again come to this slide. Here this is a given point we have enlisted. Now from the chart here we have got the temperature, that is a TD3 21 degree Celsius. So that we have written here. Now with the help of these two temperature we can find the temperature of point number 2. So for that purpose we will use here formula, that is a efficiency formula, humidifier efficiency formula. A humidifier efficiency formula is what? Here is a process humidification shown 1 to 2, that is a actual process, and 1 to 3 is a ideal process. So actual process divided by ideal process. So here we will take difference in a dry bulb temperature of actual process, that is a TD1 minus TD2 divided by temperature difference, dry bulb temperature difference for the ideal process, that will be what? TD1 minus TD3. So putting here value, here we are given humidifier efficiency 0.75, TD1 temperature, that is a 37, TD2 we have to calculate, TD1 37 minus TD3 obtained from this chart, that is a 21. So doing this calculation, we find here a TD2 temperature, that is a outlet air temperature, dry bulb temperature, 25 degree Celsius. Now in the numerical, we are asked to mention the outlet condition. Now condition can be mentioned with the two parameters. First parameter we have got here, that is a dry bulb temperature, 25 degrees Celsius. So with the 25 degrees Celsius, if you locate this point on the chart on this line, then we have to find the relative humidity what we get here, that is a phi2. That will be here, that we will write here, then we will get the total answer. So for that purpose, again we have to go to the psychrometric chart. So on a psychrometric chart, we have obtained the temperature at outlet 25 degrees Celsius. So this is a 25. From this 25, if you go and will reach here the intersection point we will find, this will be point number 2. And here if you see this relative humidity line passing through this, so this will be of 70%. So here we will find RH at outlet, that is 70%. So here from chart we get 0.2 phi2, that is a 70%. So this we have to mention in the answer. So here 70% RH. So we got this first answer, that is a condition of outlet air from the humidifier, DBT 25% and relative humidity 70%. Now the second answer is asked, that is the amount of water required to do the humidification. So for that purpose, here if you see, this is the point number 1. From this point number 1 we have to project a horizontal line. Also here from point number 2. So here this is a specific humidity scale. On the humidity scale, value of W1 and W2, these two values we have to obtain from the psychrometric chart. So let us see now here point number 1 and 2. So from point number 1, if you proceed in the right side direction, it will come here, and from point number 2 it will come here. If you see here the value of this point number 2, specific humidity, we find here value 0.014. Unit is kg per kg of dry air. So this is a humidity of point number 2 at the outlet of the desert cooler. And entry point here, if you see this point location, it comes between 0.008 and 0.010. So this is 0.009. So W1 comes 0.009 kg per kg of dry air. Now these two values of specific humidity at the end points of the process humidification 1 to 2, these two we will use for the calculation of amount of water required to carry out this humidification. So for that purpose we will use the formula, that is m dot A means mass flow rate of air multiplied by this specific humidity difference. Now in the numerical we are given volume flow rate, that is what 10 cmm, but here we need, that is m dot A mass flow rate. So that is what V dot upon specific volume, at point number 1, means we have to find specific volume at this point. So for that purpose we have to do the process. The process is what? Draw the line parallel to the specific volumes about the both side of this point. So here you will find the specific volume line, this line, and here one line also you find. So to these lines you draw the parallel line. This line, if you observe, it is coming between or half, at the half of these two. So here is a 0.9 specific volume, here is a 0.88. So an specific volume of this point from the chart we will get 0.89 meter cube per kg. Now this we have to use in the formula, that is mass flow rate of air. So in the calculation, under the second head of the calculation part, water required in humidification process, m dot A into W2 minus W1, which is further V dot 1 divided by Vs1 into W2 minus W1. Now why W2 minus W1? So here if you see, the process is from 1 to 2, so higher humidity is at 2. So here 2 minus 1 we have to take. So now value of V1, that is a air supply given, that is given in 10 cmm, means meter cube per minute, means we have to convert that value in meter per second by dividing it 60. So 10 by 60, that is a meter cube per second, divided by specific volume that we have obtained from the psychrometric chart, 0.89 meter cube per kg. This we have obtained from the psychrometric chart. So this we will put in a bracket, specific humidity values obtained from the chart. So thus, if you do this calculation, then we will find here this humidification which is carried out, that is coming 9.3633 into 10 raised to minus 4. Now unit of this will be kg per second, because here we are using this mass flow rate in a kg per second, but we are asked this in a kg per hour. So for that purpose we have to multiply this value with 3600. In a 1 hour, seconds are 3600. So if you do this calculation, then we find the answer, that is 3.3714 kg per hour. So this is the second answer, that is water required in humidification process in kilogram per hour. So in this way we have got this all the answers. Let us all these put in a output. So output of this numerical is what? Final dry bulb temperature and RH of the air we have obtained, and water required in a humidification in kg per hour we have calculated. So this was the numerical on the device used in a device, that is a desert cooler, the type of process which is carried out in a desert cooler, that is adiabatic cooling and humidification. So let us meet in the next video session. Thank you.